during the lectures, please directly like unmute and ask, or you can drop it in the chat. Though I may not be looking at the chat all the time, and I might miss them. Also, you can ask me later on the Slack, and I'll get back to you as soon as I can. Uh, and regarding some of the questions, so the most recent one was regarding how rigorous this is. So that actually ties to the first question that was asked, as in, are there any um, option to do or opportunity to do research in QFT, just QFT, like let's forget about gravity. So I like to think of it as this, that as Nabil explained, that uh, in some sense, we don't even know a proper definition of QFT. So like there is no rigorous mathematically proper definition of QFT. And for people who have seen things like the path integral, then there is no way to even today properly define the path integral. So QFT is a very active subject, and as far as the rigor goes, at least in my part of the lectures, I'll only talk about things at a physics level of rigor. So we will see what physics level of rigor means. But you're always encouraged to keep asking questions, and maybe we can try to make some things even more formal. And then regarding entanglement, I think during the second or the third lecture, we will see very briefly some things about entanglement, though not anywhere in its full glory. But yeah, so that we will see. And the third thing is the things about symmetries, global symmetries, and QFT. So that's something I think we will start seeing today, or maybe day after tomorrow. Yeah. So with that out of the way, yeah. So let's start with QFT. So whenever you are talking about things that are very fast and also very small, so as you know, when the domain of small microscopic objects is the domain of quantum mechanics, like if you want to study atoms, nucleus, and all that, you have learned it in your quantum mechanics course. But if you want to study something that's very fast, like close to the speed of light, then the domain there is of special relativity. So in some sense, when you try to combine quantum mechanics with special relativity, what you end up with is what's called quantum field theory. And I will now describe a simple scenario where we will see how locality builds into all this, and how locality uh, comes into the fray. And that's why, in the slides, when Nabil mentioned that you take quantum fluctuations and you add locality into it, in some sense, you get quantum field theory. By the way, I remember there was a question in the chat that like Nabil was speaking a bit too fast. Are people okay with my pace of speaking?
Yeah, absolutely fine,
Okay,
sir.
perfect. Okay. Okay. So if you get confused somewhere, then please do let me know. I'll try to slow down. Okay. So now let's think about the thought experiment. So imagine that you are in your room, and there are like n positive charges with charge small q. So everybody can see my iPad too?
Yep,
Okay,
visible.
perfect.
Yes.
Okay, so imagine we are in this room, and there are n positive charges, each with charge q. So let's say at time t equals t naught, uh, the net charge is n times q. Okay. Now imagine that let me call this point A and point B, that at some time t equals t prime greater than t naught, what I do is I delete a charge from this point, and at the same time I create a charge at some other point A prime. Okay, and I do this at the same time. So you see that this process uh, somehow preserves the conservation of charge. Like uh, at every point in time, charge was still conserved, right? So, but there is a flaw in this argument. Uh, Anybody would like to take a guess, like a quick guess? Like, what's the flaw in this argument?
Okay, so maybe the quantity of charge is staying constant, but the positions are changing. So maybe that's the problem.
No, but that's still fine, right? Because from the point of view of my system, where my system is this whole box, the conservation of charge still holds, right?
Yeah.
Yeah.
From the aspect of quantity, it does.
Yeah. So yeah. So even if their position changes, I mean, it doesn't affect the net conservation of the charge.
Yeah.
So I'll take one more response. But thanks for your response. There are some things on the charge can't appear instantaneously. So there's a yeah by Nafis and Rana. So exactly. So they're going in the right direction. So the key point here is that I simultaneously have to delete a charge at some point and like make it appear at another point. But you see, simultaneity is a relative concept, as you know from special relativity. So when you want to write down a causal theory, so there would be a frame where there will be a time delay between the vanishing of a charge at some point and appearance of a charge at other point. So in that frame, this conservation will break. So that leads us to the notion that if you want to write down a causal theory, then you will have to have the principle of locality into it. So from that point of view, now the conservation that we were talking about can be written down in this way. So you define something as a charge density, which is this quantity J0, and this is like the current density. So if you would have taken a course in electromagnetism, so this is something that's called the continuity equation. So what it tells you is that, again, consider the box, but let's now draw it like a sphere with no funny corners. So if there's a charge here, then it can only leak out from the point A by a flux that goes through the surface of the sphere. Okay, so that's the content of this equation. So what this means is locally you have a conservation of charge, and that amounts to having this continuity equation here. So the charge can leak out from the point A through a surface as manifesting as a flux that goes out through the surface. So this means that if you want to talk about causality, then locality is very intricately related to this fact, okay? And so that's why when you take quantum fluctuations, that is the physics of very small objects, and you add on top of it locality, then in some sense you get quantum field theory. However, uh, oh, sorry, I'll improve my handwriting from the next slide. So here I just mentioned about causality implying locality, and this was the continuity equation. Okay, but from next I'll write it a bit better. Thanks for pointing it out. Okay, uh, you want me to rotate my iPad? Yeah, but I think so is it better? Is
Yeah,
that okay?
bigger.
Okay,
Yeah.
okay, cool. Thanks. Okay, so yeah, so as I said that if you want causality, then if a theory is causal, then that implies locality. However, there's a caveat to this statement. So as we argued that if you want to have a causal theory, then that gives you a local conservation law in some sense. However, the caveat is this direction is not always true, and you know this very well. So as you know that in quantum mechanics, you also can write down a continuity equation. Now, there's an exercise that I have set in my lecture notes, which is asking essentially what is this continuity equation about? Like, what is the conserved quantity there? And so that conserved quantity, that continuity equation is again a local equation. So you get a local continuity equation there. However, as you know, that quantum mechanics essentially is like let's say the Schrodinger equation. It goes like this roughly schematically. So you see that you have one derivative of time here, but two derivatives of space. So this thing in that sense is a causal. It doesn't respect special relativity. There will be instantaneous transmissions around. And we will right away see an example of this. So this means that you can have local continuity equations and local conservation laws even if your theory is a causal. So that might seem a bit counterintuitive, but the reason that you still get a local continuity equation here is because uh, in position space, the Schrodinger equation uh, is still local, okay? If you have a local potential, okay? So that's why you still get a local continuity equation. What is non-local is that space and time are not treated at the same footing, okay? And so you don't have a limit on information propagation. And we will explicitly see this. So is this readable or you need it bigger?
Yes.
That's fine. Okay. Okay. So yeah. So I will share my lecture notes after every lecture, and there will be some questions there. So try solving them so that that will help you learn the subject. And some of them will also be assigned to tutors in tutorials. Okay. So there is another question. Oh, why causality implies locality? Yeah, so that was the whole argument that I gave here. So the reason is you see that uh, we could not create or destroy charges simultaneously because simultaneity is not a relative concept. Sorry, because simultaneity is not an absolute concept, it's a relative concept. So there could be a frame where there will be a time delay between your creation and annihilation of a charge. Okay. So that means this is not a nice conservation law. And this conservation law did not involve locality. This particular conservation law, like creation and annihilation of charges, did not involve locality. So the way out is to look at locally conserved laws. For instance, if you take a charge density in some like a region of spherical region, let's say at point A, now the charge can only come out of that region only through, if you imagine an imaginary surface as a flux through that surface. So this thing is a local description of flow of charges from one point to another. So charges can't just vanish and reappear. So that's not fine in a relativistic theory, okay? So that's why I said that if you demand a causal theory, then your conservation laws will be local, right? Is that clear? I hope that's clear. Okay. Okay. So now let's move ahead. There is another reason to study quantum field theory and not just quantum mechanics. Because you see, in quantum mechanics, there was a nice property that the particle number remained conserved. Okay. So let's say you are dealing with n particles. So you perform some operations, you solve the Schrodinger equation. At the end of the day, you will still have n particles. But if you put into this whole pot the theory of special relativity and you demand causality, then as you will see, it will lead to non-conservation of particle numbers. So the way to see this is, so you know that non-relativistically, the energy is given as p square over 2m. Uh, so at times I will not write a vector on p. I'll try to be consistent. Okay. So where p is the usual three momentum vector. But if you are looking like in a relativistic theory, then as you know, the correct equation is this. And now if you expand it for uh, very small momenta, then you can write this as like this, okay? So you see that, and here m is the rest mass. So you see that the rest mass energy is like a contribution on top of the usual kinetic energy. Now, we know that special relativity tells us from the formula of rest mass energy that if you have enough energy in a system, then you can create particles out of it, okay? So let's say you take a box and localize energy inside it. So you might, and like there's a non-zero probability that you will be able to create some particles, okay? So let's say you are interested in charge particles. So you can create charge particles just from energy. But at the end of the day, charge should be conserved. So with the particle, let's say with a positive charge, you should also create a particle with a negative charge. So we will later in the course call this particle-antiparticle pair. But that's what the intuition behind particle-antiparticle comes from. That even though you can create particles out of just pure energy, they should always come in pairs so as to preserve or lead to energy conservation at the end, like charge conservation in this case at the end. So because of that, if mc square is the amount of energy that creates one particle, then if you have energy up to twice of mc square, then you can create a particle-antiparticle pair. Okay. So imagine again our box of length L. So if you condense 2 mc square amount of energy into it, then you will be able to create particle-antiparticles out of it. Okay. So there is a way we can try to estimate what should be the dimensions, what should be this L, how small should you take L so as to create a particle-antiparticle pair. So heuristically, we can argue this, and the argument goes like this. So as we said that the amount of energy needed is this. Now let's say you know that the uncertainty principle, the Heisenberg's uncertainty principle tells that change like uncertainty in momentum q and uncertainty in position should be lower bounded by h bar over 2, which is not 0. So you can't simultaneously measure the momentum and position of a particle to arbitrary order of accuracy. So now, because the box has length L, so it means that, yes, somebody wrote in the chat, Compton wavelength, that's exactly the argument. Let me continue. So the uncertainty in momentum because of the size of the box L will go like this, okay? Because delta Q can at max be L. Now, you see that if you take the equation that we wrote here, let's call it star. So now if we consider star and then we expand it for ultra relativistic momenta, then what we get is the uncertainty in E can be written as C times the uncertainty in P. Okay. And that gives us C upon 2L. Okay. Now, this means that we know that now this should be equal to 2mc square. So that implies that L should be of the order h bar upon mc. And this is what is called as the Compton wavelength of a particle, as was pointed out in the chat. And for an electron, this is about, so for an electron, this is about 10 to the power minus 12 meters. Okay. Right. So you see that if you condense energy inside a box of length L, where L matches the length of the Compton wavelength, then you will be able to produce a particle-antiparticle pair. So this shows us that Uncertainty principle together with special relativity implies that the number of particles in your system could that there's no conservation quantity for that. Okay. Uh, I forgot something to mention before the start of the lecture, but that's important. So let me mention now. So I will be following the following conventions. So the Minkowski metric for me will be this diagonal matrix. So this is the mostly minus convention. And mostly I will use natural units where I will set C equals H equals 1. Okay. Even for there's a question. Uh, Sorry, I don't understand the question very much. Okay, but we can discuss that later. Okay, so yeah, so that's what. So that's why that's another reason why quantum mechanics cannot handle uh, these things because there the particle number remains conserved, but in nature, because we know that uncertainty principle is true and nature is relativistic at high energy length scales, so you have this heuristic argument that the particle number is not conserved. Now, coming back to as I had promised that we will see why. Schrodinger equation was non-local in the sense that it allowed instantaneous propagation of information. So we will see a concrete example now. So we will discuss. Sorry, there is another question. Yes, exactly. So the particle numbers is not conserved. Okay, but we will say more about it when we introduce the notion of real and virtual particles. Okay, so carrying on. So we will talk about again non-relativistic quantum mechanics, but we will compute propagator. So we will compute a quantity which is called the propagator. So the quantity that we want to compute, let me denote it by G. So it's the overlap between an initial state and a final state. Sorry, there is no space here. Let me take it low. So what does this? So this is an overlap between an initial state xi and a final state xf. And the thing that this measures is if you create a particle at xi and then you measure it at some position xf. So what's the probability amplitude that you measure the particle that was created at xi at xf after some time tf minus ti? And so we will be interested to compute this quantity. So mod g square is the probability of finding the particle at xf and time tf. Okay. So let's compute this quantity. So the things that we will use here will also be needed when we compute propagators in QFT, the Feynman propagator. But we will keep it a little bit simple now, but we'll go in more detail when we do the QFT computation. So let's start. So first of all, as you know from quantum mechanics, that in momentum space, you can write down the wave function as a plane wave. So this is the plane wave basis. Okay. So with this, you can write this quantity G as an integral over momentum space. Delta T, and delta T is Tf minus Ti. And note that I wrote down the expression for the relativistic energy here. So I'm trying to take quantum mechanics and then hand feed into it the relativistic version of the energy. But as you will see, this also won't be enough, and this will lead to some bad stuff. So the way to reach this point, so I'll just leave it as an exercise because you would have done it in your quantum mechanics course. So the way to reach here is to use the resolution of identity. Okay, so you insert a space of these wave function bases that we constructed, and with that you can write down the this quantity G, this propagator, as an integral in momentum space. Okay, so if you like, this is an exercise. Uh, just to be clear, the resolution of identity, by that I mean this. Okay.
The projector.
Yes, the projector. Yeah, exactly. Sorry, for some of you, all these things could be quite basic, but since I don't know, the audience that I'm speaking to, so I'm reviewing some things. But please, like, if you have any questions or any comments, do let me know. Okay. Okay. So now we are interested in computing this integral, but we want to look at a scenario where, first of all, let's set the initial position and time to 0. And also, we want to have a scenario, and also let's denote xf as x and tf as t. And we also want to look at these 2 points, the initial and final points, as to be space-like separated. Okay. So what does space-like separation means? So it means that your x should be greater than t. Uh, so and which is greater than 0. Uh, so essentially, if you want to draw a light cone, so let's say in 1 + 1 dimension. So this is my t, this is my x, and this is like plus t, and this is minus t. Uh, sorry, t equals minus x, t equals plus x. Now, the scenario that I'm considering is lives here, okay? Because my spatial part is greater than the temporal part, and that happens in this part of the region, so that is outside the light cone. So hence objects are space-like separated. So it's like my xi is somewhere here and my xf is somewhere here. Okay. So for this scenario, let us now compute this quantity which I'm calling the propagator g. Okay. So let's again write it simply in terms of x and t now. Okay. Now you see that this thing is has some oscillatory behavior because of the cos and sine functions, because of the trigonometric functions here. So one might think that when you take p to infinity, because of this oscillatory behavior, it there could be some problem in convergence of the integral, that there may not be a smooth limit of this quantity, this integrand, when you take p to infinity because of this uh, function here, which involves a trigonometric oscillatory function. But the way to remedy that and the way to see that it actually is fine, uh, it's actually fine, is to uh, consider the complex plane. So this is the plane of P, and we what we do is, so you see the integral is actually done on the real line, but what we can do is slightly tilt the real line uh, upward, like deform it upward by some angle epsilon. And if you do that, then you see that you can write uh, EIPX um, minus I mod PE as e to the power minus T mod P plus IPX if P is positive, and e to the power minus T mod P, sorry, plus T mod P minus IPX if P is negative. Okay. So it means that we put the vector signs here. That now, if you take P to 0, you see that this exponential now comes, this oscillatory function now comes with an exponential suppression. Okay. So you can safely take this limit, and the integrand will be convergent. Okay. So the idea was that you shift P from the real line, like totally real values, to a little bit of complex values. And then you expand the e to the power IPX with that new P that's slightly complex, slightly imaginary. And you can then show that it will always come with exponential damping. So that ensures the convergence of this integral. Okay. So with that out of the way, uh, so at least we are guaranteed that G is a nice convergent integral. Now, you see, there is a second problem or a second difficulty in evaluating this integral, and that is hidden in this square root. So now, if you recall from complex analysis, and for people who are not familiar, I'll try to give an appendix in my notes to some things about complex analysis, but I won't review them now. So I'll assume that you know a little bit of complex analysis. So whenever you see a square root like this, so what you get is something that's called a branch cut. Okay. So there will be two branch cuts. So one for the positive sign of the square root and one for the negative sign of the square root, because it's like a plus minus here. So in this calculation, we'll focus on, we'll choose the positive branch. And recall that we had this deformed contour with epsilon. And at the end, we will take epsilon to 0. So we can, using this branch cut on the positive imaginary axis, we can deform the contour all the way, and we can reduce the integral to something like this. Okay. Okay. Let me put the directions here, because recall that this was an integral from minus infinity to plus infinity. So it means the uh, contour that you will be considering C will go around the branch cut. Okay. And this point is P equals IM with M positive. Okay, that follows from here. Okay. So yeah. Also, if I am moving my screen on the iPad too quickly, like if I do this quite fast, then do let me know, okay? So that I can give you time to see the argument.
Okay.
Okay. So yeah. So now we want to evaluate this around this branch cut. So if we do that, so we want to evaluate from m till uh, plus infinity, so plus I infinity. And so we take p as I lambda, and p equals im is this point. So with that, you can do a change of variables inside your integration, and what you get is this quantity. Again, people who are not familiar with complex analysis, this could be quite fast for them. For that, I'll refer you to the appendix in the lecture notes. Otherwise, this is quite straightforward actually. So what we get is this g lambda e power minus lambda x. And you can write down these exponentials in terms of sine hyperbolic, as you know, and that gives you this quantity. Okay, great. So now you see that if you do mod g square of this quantity, then this I goes away. This I goes away. So you get this quantity as something greater than zero. So this is non-zero. Okay. Scroll down slowly. Okay. Is this
Sir,
slide?
we consider complex analysis because of hyperbola.
Sorry, I didn't understand that. Consider complex
Um,
analysis.
uh, I asked, we consider complex analysis because of hyperbolic equation, since like you write since.
No. So the cinch comes from the fact that so the cinch that you see here, that comes from the fact that when we were solving this function, mm, solving for this integrand, like evaluating this integrand. So the exact expression of the integrand with p now taking imaginary values like I lambda, it gives you an exponential. So when you add or subtract exponential, you get the cinch. So the complex analysis doesn't come because of the cinch. The complex analysis comes because this quantity, this square root, this quantity has a branch cut in the complex plane. Okay, so I can, as I said again, I won't be reviewing it in detail here, but I can give you a quick argument as to why these things come about. So you know that um, any complex number can be expressed like this, right? Up to a quantity r, let's say the modulus. Now you see that uh, if you take the log of this, and let's take unit vector. So let's forget about r. So this is just uh, I theta. Okay. Uh, no, sorry. I should keep the r. Yeah. So this is I theta plus log r. Now you see this guy is actually the same up to theta going to theta plus 2 pi. Okay. So you change theta by 2 pi, you get the same quantity z. But this guy is not that, because if you change this by 2 pi, then this function, this log function, uh, picks up an extra 2 pi. So this means that if you look at again the complex plane, okay. Uh, so let's say this is my branch cut now. So once you circle, that's and you go over this side, so you pick up an extra 2 pi I in a log function. Okay. This thing for a square root gives you branch cuts in the imaginary axis, because of why? Because of this extra like you have two separate disconnected branches. Okay. And so this is why complex analysis comes about, because now you want to do an integral. You see that this was an integral which involved complex numbers, and we also deformed the contour slightly to make the momentum a little bit imaginary, right? So we want to do complex integrals now, but complex integrals should be carefully handled because they are multi-valued. Okay, because of this, one of the reasons being this, like functions like log, functions like square roots, and that's why you pick up phases. And then there are nice theorems that help you solve it, like Cauchy theorems, which I will uh, write in my lecture notes. So the sign hyperbolic appearance has nothing got to do with complex analysis. Complex analysis comes about because you are looking at multi-valued functions when the argument is a complex number. Okay, the sign hyperbolic comes
Thank you,
because you have
Professor.
x.
Got it.
Yeah, no worries. Okay, so where were we? Yes. So as I said, so this quantity is the greater than zero, so it's non-zero. But that's something not nice, right? So what we did in this exercise was we took quantum mechanics and we took the relativistic energy. Okay, so it's like taking Schrodinger equation, but instead of the Hamiltonian, you substitute it for this thing. Okay, the relativistic version. But even when you do that and you compute the probability amplitude, for a particle travel which was at point xi and then goes to point xf, you see that even if they're space-like separated, there should not be any transmission of energy or communication between them. They still do end up communicating. So we see that there outside the light cone there is some information propagation. So we see that outside light cone there exists information propagation, and that's not good. That's a causal. Okay, so if you start having those things, then you will end up with like, as you see in many I don't know, in time travel movies, you'll end up in many time paradoxes. You can go back in time, you can kill your grandfather, and then you can ask who are you for the rest of your life because your father was never born and things like that. Okay, so these are not nice things. So that's again another reason why we need to be very careful the way we want to incorporate special relativity into quantum mechanics, and that's how we will go to QFT. Okay, so with that, we will conclude the discussion on why relativistic quantum mechanics is inadequate uh, when you want to look at things that are very fast, where relativity cannot be ignored, and very small, where quantum mechanics cannot be ignored. Okay, so now because we saw that particle numbers doesn't remain conserved, so instead of uh, point particles, which you studied in classical mechanics, we will study what are called fields. Okay, so fields, as you know from your electromagnetic course, it's essentially a science. So it's rigorously speaking, so it's some function f which maps a point in space-time to the real number set. Okay, or the complex number if you want. So this is what I will denote my space-time as. And so my space-time is given by the Minkowski metric, as I said. And this one corresponds to this one here, and this 3 corresponds to these 3 minuses. So the 1 corresponds to the time, and 3 corresponds to the space. So we are in 4-dimensional space-time, so that's the notation for R13. And it's a function that at each point in space-time, it gives you a real number or a complex number, depending on what you want to study. So that's what a field is. Okay. And for instance, electric field, as you have studied, or magnetic field. So at each point, you have the electric force. Okay. Uh, and so I'll just share an historical thing here. So in fact, the field was first coined by Faraday. And the reason behind the concept of field was he was working in some farms, and then he understood that you know electromagnetic field has to be described with fields and not particles. And as you know, the reason is because it is the first relativistic theory, classical though, but still the first relativistic theory that we know of. So he thought that, like in a farm, you have like plants, or you sow the seeds in a grid-like structure, like which are uniformly spaced out. So somehow this gives you the feeling of a lattice. Okay, So you have a lattice structure. And then he somehow thought in his head that if you take the lattice spacing to 0, you go to the continuum limit. So that's where the word field comes from. So it essentially comes from fields in the farm. Okay. So it's very apt, that naming, unlike many other things in physics. So it's a very apt justification. So yes, so as I said, uh, because we want to study a system where a theory where particle numbers need not be conserved, so we should start it with infinite degrees of freedom. So now, if at every point in space you assign a real number, so essentially you have infinite degrees of freedom because there are infinite uncountable points in your space time. Okay. Another example is like temperature field. So it's a scalar field. There are no, we will discuss what are scalars, but there are no index. And when people talk about, in weather report, they say that in a country, the north is like 10 degrees, the south is like 30 degrees, or something like that. So essentially, they're talking about how this temperature field varies smoothly across each point in space-time. And the degrees, the 30 and 26, they live in this image space, this R. So in that case, it's real, but you'll also encounter complex fields. Okay. So then, a very brief thing about quantization, like a very brief summary of QFT is you just take, like you go from particles, as we said, you go to fields, and then, uh, like in quantum mechanics, you go from functions to operators. So then you will go to operator valued fields. And these are all again just to give you a grand picture. We will go through all of this in uh, uh, much detail later. And then what you do is you impose uncertainty relations, okay? Like Heisenberg, like uncertainty relations, okay? Or as you know from your course in quantum mechanics, that this is similar to saying that you impose these equal time commutation relations. So there are these, sorry, let me write about in the language of momentum and position. So imposing equal time commutation relations is the same as imposing Heisenberg uncertainty relations. Okay. So once you do this, you get yourself a theory of fields which is quantized. Okay. And for some weird reason, this was what was called second quantization. And actually, it's not that weird, but it confuses because there's nothing being quantized twice. All it means is the first quantization is going from particles to operators and imposing uncertainty relations. The second is going from fields to operator valued fields and imposing quantization. And surprisingly, this notion is still there. And this is why I said that field was an apt justification for a physical term. But as you see, second quantization is not that great. For instance, people who do string theory, they talk about first quantized strings and second quantized strings. So this notion is still there. Okay, we are stuck with it. Okay, so with that, we get what is called a quantum field theory. So that gives us quantum field theory. And there are many important consequences that we will get from playing with all these stuffs. So let me note down them. So one of them is uh, there will be many distinct particles like electrons, protons, neutrons, but also indistinguishable. Okay. So for instance, like before QFT, we used to think of protons, electrons, these are as different objects. Okay. But we can class all of them. Again, all these we will see later. So we can class all of them as something called fermions. Okay. And then there are other particles which are like, so this is mostly what will be matter fields. Okay. So when you will quantize matter fields, they will give rise to what are called fermions. And then there will be something called, sorry, I was writing scalars, bosons. So, and these will be your force carriers. Okay. So they will be responsible for interaction between particles. Okay. And now, in some sense, a proton is different from an electron, but in some sense it's also similar in the sense that it's fermion. So there can be different species of particles grouped into fermions and then different grouped into bosons. Okay. Now, the tied to this, there's something called a spin statistics theorem, again, which is something that we will see and in fact derive. So we will see that when we combine quantum mechanics with special relativity, that will force us that a certain spin of a particle should uh, obey certain kind of statistics. And by statistics, I mean if you interchange the position of, let's say, some particles, then you can interchange them normally, or you have to interchange with a phase that gives you a minus sign. Okay. So again, that's something that we will see is built into quantum field theory, and the reason is in a very uh, nice way, causality or demanding relativistic invariance gives you this. And the third thing, as we briefly alluded to, was there are something called antiparticles. So antiparticles are some things that are exactly opposite of particles, except, let's say, like electron. So the anti-electron, which is also called the positron, will only have the charge difference. Uh, Otherwise, the mass and every other thing, every other property will be the same. And that has something got to do with a very nice symmetry of the theory called charge conjugation. And in some sense, as we also argued in the beginning, this has got to do with charge conservation of the universe. Okay. So if you create a stream of particles from a lump of energy, then these stream of particles should be particles and antiparticles just to ensure that the net energy is still, the net charge is still conserved. And yeah, so that's all about QFT. Now let's dive a bit deeper into special relativity. Yeah. So because we need to understand special relativity a bit better. So again, this could be something that is known to most of you, but I hope there will be some, like a few bunch for which this will be interesting, but bear with me if people know this already very well. Okay, right. So yeah, so when we talk about special relativity, we talk about Minkowski space, we talk about Lorentz transformations, and these form like the core of special relativity. And the way Lorentz transformation is taught to us is like you compare two frames, uh, like O and O prime, and O prime is moving with some uniform velocity v, and then you derive some linear transformations between these frames based on the two postulates of special relativity. So let me write down the postulates. So the first postulate is the uh, postulate of relativity, which says that laws of physics are same in all inertial frames. So by same, I mean if you conduct an identical experiment in frame one, and if you like identical experiment should give you the same outcomes, whether it is frame one or frame two. The second thing is the constancy of the speed of light. So this says that c equals c prime. So if c is the speed of light in one frame, it will be the same in another frame. Okay. And now note that. So if you write the speed of light, let's say we are in 1+1 dimension. So 2 implies that dx by dt is equal to c, then it's also equal to c prime, which is dx prime over dt prime. Okay. Now you consider these as differentials, okay, like small differences in time and space, and then you multiply them, and then you square this. So what you get, c square dt square minus dx square equals c square dt prime square minus dx prime square equals 0. Okay. So we see straight away that we get a quantity that is the same in all frames. Okay. So this is a scalar quantity which is same in all frames. So by definition, this is a scalar. Okay. So that implies this is a Lorentz scalar. This is also called the invariant line element. However, this is an exercise. This bit of a hard exercise, but this is for you to try out. This thing that I showed to you now, that how to get the invariant line element, this invariant line element, uh, just using the constancy of speed of light postulate. This actually, there are some things which I disregarded at the moment. So what I showed to you, that this object is invariant under like in both the frames. So this is the same in both the frames. But what I didn't show you, that what I didn't show you is this. Okay. So I didn't show you this. I showed you this is equal and that equals to 0. Okay. So now I will leave it at that to think about it more. Like for some of you, you might think that what's the difference? But there's a very crucial difference. Okay. And that difference is very vital. So I don't want to go on and on this. Again, if you get stuck in any of the exercises, you can write to me on Slack and I'll be more than happy to discuss. Okay. So as we said that there's something called Lorentz transformations. So a Lorentz transformation is a linear transformation among frames, inertial frames, such that this quantity, this equation holds. Okay, so let me call this star prime. So this equation holds. Okay, where so if this is true, so lambda is a Lorentz transformation. Okay, and as I said, this is a linear transformation. So linear transformation means if you are in X prime and you want to relate it to X, then a linear equation is this, right? So it's like y equals mx plus c. So this is what the general form of the transformation will be. However, we will first look at transformations with a equals 0, and then we will look at transformations with a not equal to 0. Okay. So for us, a Lorentz transformation will just be a quantity with a being 0. And then when we add in a, we will call it a Poincare transformation later. But for now, it's Lorentz transformation. So that's why even though there is the word linear here, we will just restrict ourselves to the subset of transformations with no non-zero a. Okay. So that's the definition of a Lorentz transformation. And in the beginning, I said that normally when we are taught special relativity, we just take these two frames. One is moving with a uniform velocity, and then we do all sort of physics with it, like we study relativistic kinematics and all this. But somehow we get the feeling that this boost that we talk about, that's the only Lorentz transformation out there. But that's not true. The Lorentz transformations are a much bigger group, as we will see. And boost is only a sub part of that. Okay. Okay. So that's what the definition of a Lorentz transformation is. And just to add to my point that there are many other Lorentz transformations which obey this definition is you can consider rotations. Okay. So let's say you rotate by an angle theta. So again, O and then O prime. And here again, you can show that this quantity is preserved. Okay. So in some sense, one way to understand this intuitively is that in Newtonian mechanics, in classical mechanics, such a quantity was given by the Euclidean metric. Okay. So that quantity was just this guy, right? So that, what did that do? That preserved. So if you take a frame and you rotate it, you still get the same quantity because let's say the length of my phone doesn't change if I rotate it. Or if you translate my phone to a different place, then also it doesn't change. So rotations and translations was what gave you the symmetries of uh, Newtonian physics or classical physics. Okay. Okay. Now this is a good point to talk a bit about something more mathematical. So as I said that throughout this course we will do things uh, at a physics level of rigor, but we will try to motivate many mathematical things from physical necessities, let's say. Okay. So one of the concept is what is called a group. Okay. And again, many of you might know this, so it could be quite basic, but let me go ahead. So when you want to discuss symmetries in
You
your
had a
system,
lecture on group theory, preschool lecture.
okay, but I don't know how much was covered. Like, did you
No.
cover Lie?
Linear.
Like, yeah, I don't know if you covered Lie algebra and all that. So
No, we didn't.
so I think it would be a good thing if I just start with groups and then go to Lie algebra. I think that is more smooth than just talking about Lie algebras directly. Okay, so whenever we talk about symmetries, so let's just look at translation. So you see that translation is a symmetry of classical or Newtonian physics. Let's say the length of my phone doesn't change. So now you can argue all the axioms, and now that I know that you know group theory, all the axioms of group theory can be motivated from looking at what happens when you translate something and the physics doesn't change. Okay, so let's say the first axiom of group theory is closure. Okay, so a group is a tuple of a set G and a binary operation star. So closure means that if you take two group elements and you compose them with the group operation star, then you still land in the group element. So it's like if you take two translations, one after the other, then the composition of two translation is a translation in itself, right? So that's what closure is. Then what is called associativity. Okay. Again, if you translate two things first and then a third thing, so concretely this is this. So I think I can be a bit fast here because you already know all of these things. So this is what associativity is. So you translate 1 and 2 by 1 and by 2 and then by 3 is equal to saying you translate by 2 and 3 first and then by 1. Then the third thing is the existence of an identity element. So it's like if you translate this way, then you have, sorry, the identity is that you do nothing. Okay, you translate by zero distance. So that's what an identity is. So there exists an element such that G star E star G equals G. And the fourth thing is the existence of an inverse. Okay, so for every G, there exists a G inverse. So you translate this way, the example that I was telling in the identity case. So I had inverse in my mind. So you translate this way, and then you translate by minus A, then you go back to the same point. Okay, so that's the inverse of translation. So you see, the core axioms of group theory are already satisfied by a translationally invariant system. So, and as you know from classical physics, whenever you have a translationally invariant system, uh, your linear momentum in the system is conserved. Again, we will see this in the field theory notation when we discuss Noether's theorem. So symmetry, conservation laws, group theory, they are tied to each other, and groups give us a natural playground to discuss symmetries. Okay. But because I motivated it from translation, which I happen to know was a group, and I landed up with symmetries, this doesn't mean that there cannot be symmetries that are not captured by groups. Okay, so this is just something that I'm hinting at, but we won't discuss this throughout the lectures or anything. Okay, so symmetries are even more general than groups, but it turns out that groups do give rise, do capture the notion of symmetries in a very simple way, just like we saw in translation. Okay, good. So now your exercise is, which is again there in the lecture notes. So all the exercises are there in the lecture notes. So show that uh, this lambda that
Exercise, you mean
satisfies.
homework? Homework?
So, sorry?
By exercise, you mean homework that we have to submit?
No, no, no. These are not homeworks. These are just for you to try out. However,
Okay.
some of them I will set as homeworks. Okay. So at the moment, I have not like charted out which of these exercises will be homeworks, which will be not. So you just keep trying
Okay.
out. So,
All
so
right.
if you are lucky and if that exercise turns out to be a homework, then you would have already solved it. So it's an added bonus. But yeah, at the moment, these are just exercises for you to learn the subject. Okay. So show that the
Professor,
lambda. Yes.
how group 3 is related to symmetry?
So the way we argued that is, as we said, that imagine that I want that this is my phone, and you know that if I translate the phone by something, then the length of the phone still remains the same, right? So let's say you are doing an experiment to measure the length of the phone. If you translate it by a distance a, the length is still the same. So translation is a symmetry in this case. Now I argued that what are all different properties to define translation. And as I said, that if you take two translations successively, you get a translation. So that is the closure property. If you consider three translations, but in this way, that you translate one and two first, and then the three, that's equivalent to translating by two and three, and then by one, which is associativity. There is an identity translation, which does nothing. You translate it by zero distance, because zero is also like a group element. And there's an inverse translation. So, and then, as you know from your preschool, that these are the axioms of group theory. These are the defining properties, the basic properties that you need to define a group. And translation follows all of that. And with these minimum minimum properties, you can describe translation. So this is this whole system, which is translationally invariant, is an example where a group, which is here the group of translation, captures the translational symmetry. And hence I said that this is the way to motivate. One of the ways to motivate that group is uh, something that captures the notion of symmetries. Okay.
Thank you, Professor. Got it.
Okay. Okay. So as I said, your exercise is to show that these lambdas that satisfy this equation, star prime, they indeed form a group. Okay. Uh, so that the lambdas form a group. And because, as I said, that these lambdas are linear transformations, so you can take lambda to be some 4 cross 4 matrix, because every linear transformation, as you know, is a linear map, is a linear map in the sense of linear algebra. So you can take lambda to be this 4 cross 4 matrix, uh, and that satisfies this star prime, and argue that they indeed form a group. So you have to show that all these properties are satisfied. Okay? For a generic Lorentz transformation, not for boost, not for rotations, translations, for a generic lambda. Okay. Okay. So from this exercise, we learn that the set of Lorentz transformation under the usual matrix multiplication, they form a group. And that group is denoted as O13. Okay. Again, this one is for the minus, and the 3 is for the space plus. Okay. Probably this is something you would have seen already. Now, you know that the defining property star prime, that we can, from that, we can conclude that if you take the determinant of both sides, then determinant of lambda square uh, gives you times determinant of the metric gives you the determinant of the metric. So this means that determinant of lambda equals 1. So this means that there can be Lorentz transformation with +1 is determinant and -1 is determinant. Okay. However, as we discussed in the axioms of group theory, the identity has to remain in the group. That's one of the defining properties. So it means,
Yes.
so if we separate these to two parts, det of lambda is +1 and det of lambda is -1, then the identity lives here, okay, not here. So it doesn't live there, okay. So it means this part has the potential to be a group, a subgroup, okay, in this case. But this part is not a group, okay. So you have O13, which is the Lorentz group. So the part which has the determinant 1, because the identity matrix has determinant 1, that lives in that part. That doesn't live in the disconnected part, the other part. So this other part has no way to be a group. But this side is what is called the proper Lorentz group. Okay, the proper means the determinant is 1. Okay. 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 Now I realize that I'm going quite slow, but it's the first lecture, so that's okay. 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 So as we argued that in this part where determinant of lambda is 1, there exists the identity element. Okay. So the identity element in this case is just the identity matrix, which is just 1, 1, 1, and 1. Okay. Now we can ask ourselves some things. Okay. So let's first study this part, which has the potential of being a group. Okay. This we'll study later, because at least we know the identity living there. Okay. So just like in physics, and because this is also a course on locality, so we will try to play around the identity. Okay, what we can gain about the structure of transformations in this part. Okay, so we have the identity here sitting on its own. Now we want to consider a small enough neighborhood around identity. And we want to see what kind of structure we can gather about Lorentz transformations that are very close to identity, but not identity. Okay. So the way to do that is this. So now we want to look at transformations close to identity. Okay. So the way to do is, so lambda we were denoting as the Lorentz transformation. So let us consider this kind of an equation. And let's say that, sorry, let me put in an epsilon parameter here. So now you can expand this as 1. So this is the matrix 1 plus epsilon times the matrix M. Okay. Or in components, so this will be, so delta will be my Kronecker delta. So this is my Kronecker delta, which is also the identity matrix. Okay. So this is the Kronecker delta symbol, but also the identity matrix. In a basis, it's an identity matrix. So, and then there are higher order terms, plus M mu nu, plus terms which are quite small, okay? Because we just want to look around 1, okay? And yeah, now if you take this, okay, this expression, and if you plug it in star prime, let me write it again here. So if you do that, then what you get is this. Okay, and that leads to the condition that the M's are antisymmetric in their indices. Okay, so we see that just by looking near the identity and what kind of transformations, Lorentz transformations live in that near the identity region, we could derive a very nice result that this transformations is captured by this matrix M, but it is antisymmetric. Okay. Now, so again, there's a question here for you to solve. So let's say you have an n cross n matrix. So how many independent components does it have? Okay. Again, as I said, these are not homework questions. These are questions for you to learn. Okay.
Yes.
Okay, good. Nice. So now let's try to look
यहाँ
at.
पर हमने लगाया बाद आता है 3 इसको हमने किया मल्टीप्लाई दो
Sorry. Okay, I think that was a disturbance. Okay. So yeah, what was I saying? Yeah. So that's an exercise. Okay, now let us try to look at some properties, what we can tell more about this matrix M. Okay. So for that, let's try to represent it. So one way to write this matrix is this. Okay. I will explain why this works. Okay. Yeah, I think the index are correct. Okay. Okay. So you see that this guy is an antisymmetric object in its indices. Now note that, and that is also clear from here, that alpha and beta in this writing M in this way is already antisymmetric. But why did this special combination appear with etas and deltas? So let me motivate that. The antisymmetric part is clear because the way it is constructed is antisymmetric. So it's manifestly antisymmetric. But you might ask why it's written in terms of eta and delta. Now note that we want to look at matrices uh, which are nice, okay? And by nice in this case, I mean Lorentz invariant. Otherwise, they will spoil what you want to do, okay? Study a causal theory. Now, delta, as I said, is just the identity matrix, delta mu nu. And eta is already Lorentz invariant, okay? So we just have these two matrices that are nicely Lorentz invariant. And we try to construct M out of this. Okay, so in this basis of eta and delta, this is what you get as M. Okay, and it's manifestly antisymmetric. So that's how you can motivate why eta and delta in this structure appears. So the structure comes from antisymmetry, and the eta and delta follows from Lorentz invariance. Now, with that, you can show something very powerful. So with that, actually, let's first look at some examples. For instance, not examples, but you can compute certain components of it. So let's say you want to look at the M01 component. So this will turn out to be this. So you can carefully work this out. Yeah. So this is how you can construct the whole 4x4 matrix for each mu and nu. So mu and nu are space-time indices, okay? And these alpha and beta, they are the row and column of the matrix. Okay, good. Now, using this relation, let me call this star 0. So using star 0, you can show that this quantity is like this equation holds. There, I'm trying to keep all the signs correct. But if you work out and you get some signs here and there, then feel free to write to me on the Slack. It's definitely that I have done a mistake. Okay. So you can show that this equation holds where uh, for matrices A and B, n cross n matrices, the square bracket defines what is called a commutator, which you might know from your quantum mechanics course. So you can show explicitly that in the form that we wrote here, star 0, that this holds. And this is what is called the Lie algebra for the Lorentz group. Okay. Now we will discuss what that is. Okay. So this is called the Lorentz algebra. Okay. Okay. So you see, there were some, let me pause and explain a bit more. There were some inputs that went into this. First input that you would have noticed that we only worked closed to the identity. Okay. Working closed to the identity helped us to derive this yellow box here, which I call the Lie algebra of the Lorentz group. Now, it gave us something that's nice. So let's talk about that. So you see, let's first note what are the operations that we are using here at the moment. Okay. So initially, we said that the Lorentz transformation, set of Lorentz, I think there's some feedback from somewhere. Yeah, it's better now. So we said that the set of Lorentz transformation forms a group, that's a Lorentz group, but there was only one operation there, which in this case was just matrix multiplication, right? But now we have ended up with a structure, this structure, let me denote this by, let me denote this by star 1. So we've ended up with star 1, which actually has two operations into it. So you see there's the plus and there's a multiplication there. Okay. So now, and all of this was obtained just by looking infinitesimal Lorentz transformations that are near the identity. Okay, we didn't do anything else. We said from relativistic postulate, this is what a Lorentz transformation is. Let's and then we figured out that it can have two determinants, +1 and -1, because group must have identity. Okay, I didn't understand that comment. Yes, group must have identity. Oh, sorry. The question was why we discard. Okay, I didn't see that. Okay, so the question was why we discard the -1 part of the determinant. The reason was, as somebody wrote in the chat, that the identity element is an important element in the group. It is built into its axiom. So you cannot have a group if you don't have an identity. Okay. And if you don't have an identity, you can't even define an inverse. So everything, all hell breaks loose. Okay, now coming back to it. So we said that there is an identity, and we said that that's the more simpler thing because we understand that's the group part of it. The non-identity we'll deal with later. It's not a group. And then we said, let's look at small infinitesimal distance away from the identity. Okay. And let us figure out what are the Lorentz transformations there. That gave us this nice looking thing in the yellow box. And we see that along with multiplication, we now have another operation, which is matrix addition, because then only we will be able to add these things, right? So now all of you are familiar with linear algebra. So that means we already see a vector space structure emerging. Okay. So previously we just had multiplications, nothing else. But then we said, let's look at identity a little bit far away from it. And then lo and behold, we get something that has a vector space structure attached to it. So this vector space is what is called the vector space near the identity, because we looked near the identity. That's what it means. And if you imagine that this Lorentz group, that O13, that we were talking about. If we denote it if we draw it like a sphere, then let's say that the identity lives here. Then what we found is the tangent space at the identity, right? Because a sphere at every point will have a tangent space, and that tangent space is a vector space. So, and again, we will discuss this more tomorrow. But what we saw is this Lorentz algebra is like the vector space of Lorentz transformations near the identity, because that's what we did. And this is sometimes also known as the tangent spaces identity. And the reason is this picture, okay? Okay. That's a heuristic way to say this. This is not at all rigorous. Again, as I said, just at the physics level of rigor, okay? Okay. So that's what gives me a Lie algebra, and we will talk more about it in detail. So if it doesn't make much sense at the moment, it's fine. But all I want you to take at this moment is how, yes, there's a question in the chat. I don't understand the picture. That's okay. There's nothing much to understand here. Okay, so that's why you can take the definition of Lorentz algebra as the vector space near the identity. Okay, you can forget about this. Okay. So let's forget about that for now. Okay. Yeah. So all I want you to take from here is that we get a commutator. Okay. A commutator structure that is satisfied by these Lorentz transformations, which are very close to the identity, and that also gives us a vector space structure because you have a commutator being satisfied, so you also have matrix addition. So the vector space structure immediately emerges from this. Okay. Now, but we don't want to sit near the identity all our life, so we want to move away from it. So we want to
I'm
consider.
sorry, can you just repeat that, please? The commutator, how the commutator translates into a vector space. Would you mind repeating that?
Yes. So
Please.
yes, no worries. So as I said, that looking near the identity, we derive this antisymmetric property. Then we wrote it using Lorentz invariant objects in this basis, okay, with eta and deltas. Now, with that, you can show if the square bracket is defined this way, which is also known as the commutator, you can show that these matrices obey this equation. So the commutator, and what I said is, for the commutator to be defined, you need operation of addition. Okay, so minus is like a phase, but essentially this is like an addition. Okay,
Addition of a
so
negative number, yeah.
yeah, so what I'm saying is this structure, like note that till this point we just had matrix multiplication. There was nothing else, but we also showed that this M satisfies this kind of an equation, which involves multiplication here and also additions. Okay. So that's what I meant by when I said looking near the identity, and we see that these very close to identity transformations satisfy as if they live in a vector space because they satisfy this relation. So that's why I said that, and not only a vector space which is equipped with a commutator structure because they exactly satisfy these commutator relations. Okay, so that's why I said,
yeah,
yeah.
Yeah,
So
got it. Yeah.
Again, we will talk more about this later, but thanks for your question. I had forgotten one thing, so let me write it here. So a vector space plus this commutator structure, let me not write like that. Yeah, plus this commutator structure is what gives you a Lie algebra. Okay. So we already see vector space. Vector space is what allows us to add matrices, but we also have the commutator structure on top of it, and that's what is called a Lie algebra. Okay. So the Lie is just the name part. You might ask, what's the meaning of the word algebra? So the meaning of the word algebra is because you see that in a vector space, you only have because in a vector, so let me rub the finite transformations part. Yeah, because in a vector space, you only have two operations. So one is scalar multiplication. So it's like multiplying alpha, living in some scalar, living in
Addition.
some, and then addition, exactly. Okay. And then vector addition. But now you also have vector multiplication, where these vectors are these matrices. Okay. So that's why you can do algebra. So that's why the name Lie algebra or Lorentz algebra and all that. And I am trying, as I said, this is again in no way for the mathematically inclined audience, this is in no way rigorously trying to justify what Lie algebra is. But I'm trying to motivate all these things just from the necessity of doing physics. We know that there is something called Lorentz transformations. We know that they form a group. We know that groups are useful in defining symmetries. Then we said, okay, one is a nice transformation, the identity. Let's just move a bit away from it, okay? And just that gave us an extra operation, operation which is this plus, and an extra structure of commutator. So, uh, and this is exactly what is called a Lie algebra. Okay, so I'm trying to motivate all of these things. Maybe I'm not succeeding, but at least I'm trying. Just from the point of view of physics. Okay. Okay. Now I think I'll just discuss finite transformations and then we will stop. So as I said, we should not be stuck to the identity all our life. So we should also look at finite transformations. And the way to do that is very simple. So we take the lambda, but now instead of the small epsilon parameter, we don't take epsilon to be small. We replace epsilon by this quantity omega. So this plays the role of, if you want, the epsilon. And this is what will be known as the parameter. So this is like the, so you can expand this exponential in this parameter. And this is the parameter of your Lorentz transformation M. Okay. But now you see that M is antisymmetric. So this implies that omega should also be antisymmetric. Okay. Sorry. And if this is not straightforward for people, then this is an exercise. Okay. Right. So now you can look at some. So this is how, if you allow omega to be not infinitesimal but finite, you can get finite transformations. Okay. So for instance, you can try to compute omega, like lambda of omega 0, 1, which will be M01, and then you just expand out this matrix, you will get this object. Okay. And then this is identity block at the end. Okay. Okay. So that's the matrix that you will get, and you will immediately see that this is nothing but the Lorentz boost. Okay. If you do the same thing for omega 1, 2, you will get a rotation. Again, these are all written in the lecture notes. So rotation in the x1, x2 plane, so xy plane, or about the z-axis. Okay. Okay. And yeah, so this is a Lorentz boost at about the x-axis. So now let's count how many transformations are there linearly independent. So you can have 3 boosts because you have 3 spatial directions, and you can have 3 rotations about the 3 perpendicular axes. So you will have 3 rotations and 3 boosts. Okay, 3 rotations and 3 boosts. So what's the net number of transformations? 6, right?
6.
Very good. So, and if you do the exercise, which I said n cross n matrices, then you will see that the number of independence component will be n into n minus 1 by 2. So if you do that in this case with n equals 4, t by 2, you get 6. Okay. And that sits well because we already showed that these objects M and their parameters omega are all antisymmetric, and 4 cos 4. So you do indeed get 6. So that nicely matches with our counting. Okay. Now let me take the last 2 minutes to talk about the determinant lambda minus 1 part. So there are some nice transformations. So tx, so let me just say t and x. So that gives you minus t and x. And in a basis, this is given as just minus 1, 1, 1, 1. Okay, diagonal. And there's also something called parity, which does the other thing. So it keeps t fixed and flips the space. And this, as you can quickly anticipate, will be just the opposite of this. Okay. You can show again that all of this preserve. So this is a bad notation, but whatever. This and this holds. Okay. So they do preserve the Minkowski metric. Okay. Right. Now, there is another thing that we do get. So is it okay if I just take 2-3 minutes more?
No problem, no problem.
Okay. No,
Please.
I was just asking the organizers, but okay,
Yeah,
fine.
go for it.
Okay, okay. So using this relation and looking at the time component of this. So if you look at the time component of this relation, so you can show that you get something like this. So this means you have two different things. So you can have this or you can have this. So this is something what to do with the 0, 0 component of the Lorentz matrix. Okay. So with that, you see, and there's a nomenclature for this. So these guys are known as orthochronous transformations. And these guys are known as non-orthochronous transformation. Okay. And you can see that this is orthochronous. So I'll just denote it by O. And this is non-orthochronous. However, this is improper because the determinant is -1, and this is also improper. Okay. So both P and T will not live in the identity part. They live in the non-identity part. Okay. And this also tells you something more. Because they don't live near the identity, they do not have any infinitesimal versions. Like the way we constructed the finite versions of these M's was by exponentiating with not a small parameter. And so there exist finite transformations, like finite translations, finite rotations. But finite parity and finite t are the only thing. There do not exist any infinitesimal version of that. And the reason is clear because they live in the non-identity section. So they're not connected to identity in any way. Okay. So yeah, so I think with that, let me conclude for today. So I'll just briefly tell you what we learned. This important part about, so I'll skip the initial motivation part, but for the special relativity Lorentz invariance part, what we learned is we argued that Lorentz transformation will form a group, and their groups are essential for notion of symmetries. We then said that there are two disjoint components, disconnected components, one with one determinant and one with -1. And then we said the group part is in the one component. So let us expand around the one component. We found some properties. We found a nice commutator relation. We found what is called a Lie algebra. That's like a vector space structure near the identity. Then we saw some examples in the -1 part. And then we argued that there are no infinitesimal way to realize them. Okay. When we will go to Noether's theorem, we will see a direct application of this. So we will consider infinitesimal translations, and we will see that we'll get some current out of it, a current which is like a field at every point, okay, and it will be conserved. But there will be no currents for P and T because there are no infinitesimal versions of this. So more we will talk about this later. But yeah, I think that's a nice summary of these things which I wanted to tell you. So tomorrow, what we will start with is we said that lambdas are linear transformations, but we had kept these guys 0. But tomorrow we will start by keeping this non-zero. So we'll also add translations into it. Now, just a last question, food for thought. So we said 3 boosts, 3 rotations. When we add in translations, how many independent components we will get? Anybody? And we will end with that.
3.
Okay, one more taker. 3 is a good answer.
6.
6 is 6. So 3 lives near the identity part. 6 is in the disconnected identity part. So it's not bad, but it's. Sorry? Yes, somebody wrote in the answer 4. It's 4. And but the guy who said 3 was thinking in the right direction. So there are 3 for the 3 space, but you can also translate along time. Okay.
Yeah.
So that's why there will be 10 components. Okay. Thank you.
All right. Good night.
Thank you, Arpit. I think the next lecture is on the 15th, so day after tomorrow.
Yes.
Yeah. No, because you were saying tomorrow. So I was like,
Oh, sorry. Oh, no. Sorry. That's a big mistake from my part. Yeah, it's day after tomorrow. It's not tomorrow.